we also define what is age. Actually, what age is gives you the boundary of an object in an image. And by boundary means, suppose you have a face image. In the face image, you can see what is eye, what is nose, and but if you see the age directly, all component of nose you will not get, right. Wherever you will find that there is a sharp change of intensity level, those part only will be visible, right. So, it is a fundamental problem in image processing. It occurs, this type of problem occurs very or we will be needing to solve in many occasions. Edges are areas where you will find that strong intensity contrast, or in the boundary line you will find there is a vast difference between the pixel value or pixel intensity value on the edge and its neighbors. So, that edge detected image, it will be a binary image type, binary image, that wherever there is an edge, you will get say dark pixel, and rest of the thing you can make it white, right, to get the skeleton of the image. So, since it is a 0-1 type things, so it reduces the space, right. You do not need to store all the information, only you can keep the dark pixels. Now, you remember that you have an image 1000 cross 1000 say image size, and there are dark pixels and white pixels. So, you want to store, I am claiming that volume of data will be reduced substantially. One way you can reduce, because you can use the bit vector. So, 8 pixel positions you can put in 1 byte. So, space will be reduced by 1/8, right. So, another way you can think, you assume that it is a sparse matrix, right, because 1000 cross 1000 means 10 to the power 6 locations, and maybe 2% sparsity is there. So, why to store all the 0 values there, only 1 values along with row measure information, row and column information. Since you are retaining only the edges, there will be certain noise and other things in any image, those things will be suppressed by your method, that has to be taken into account, and it retains the structural property. That is the most important thing in the edge, that structure will not get changed, because you are keeping the boundary informations, right. So, shape of the image is retained. So, what is your aim? Your aim is to draw a line or line drawing representation of an image, right. Now, once I give you an image, and if I tell you that draw a line over the image, only the boundary area only you will be drawing the line, rest of the things you will not be touching, right. And as you are drawing the lines, so you are retaining the shape informations. Once you are retaining the shape informations, whether it is a geometrically you increase, decrease, whatever you do, the shape will be kept same. So, shape is shape invariance, right. Another thing is that if I have the line drawing representations, I can put the color on it to get back to my original image. Now, of course, you will not get back the exactly same image, but similar looking image you can find out, right. Say, suppose I have a line drawing image, and now I want to put that how I look if I put the red color shirt on it. So, you can put the shirt design and color it, and you can find out how it looks. So, all those things possible on the edge detected image. Now, why you need the edge detection algorithms? So, we need from the edge detection, you will be getting what? Image outlines. Now, once image outline is available, as I told you that you can do lot many work. One is that as I want to put the texture or color on it, or if I want to put some other information on this, suppose I want to put a mole and check how it looks, you can do all sorts of things. Then you can enhance the image. How? What I do, I will put the boundary lines, I will put the very dark color on it, and then I superimpose on my previous original image, then the boundary will be more sharpened, right, more highlighted. Second one is that it will be very useful. This one example I can give you recently what we are trying to solve. I have the vein data. Vein data means hand vein. I have taken the data. Now you have the flesh on it, and the veins are inside the flesh, right? It is not visible. But small lines are available. You check that the lines are available. Now I want to get the features of these veins. Well, how can you do it? Because whatever way you do it, that hairs are also coming in between, then these features of this skin also will be coming in between. I don't want the feature on the skin, because I want the feature on the vein. So what we are doing, that on the grayscale image, we obtain the edge of these veins and then superimpose on it. Now the vein information is more highlighted than your skin and other hair and other things. Now we are extracting the feature from there. Now there are some different feature extraction techniques. So we are trying to get some feature extraction from there, and we are getting it very good way. Next one is the segmentation. See, I think in last class also I gave it one example, that if I have the edge with boundaries of some object, then I want to get only the object, I do not want the background, or I want to get the partial objects, say it is a composition of two objects, I want one object, the other objects can be eliminated. So I can separate them out through the edge detected, from the edge detected image. And next one is the more useful one is the registration, image registration. There I have the two structural property or two structure, right. Now I want to register them, I want to superimpose some part of it. So the structure is there. What I do, that I have the two traced image, just I put one on the top of the another one to see that whether they are matched or not. That is known as registration. So these three are very important operations we generally perform on image, and if I have the edge detected image, then it is becoming very easy to implement. So this is an ideal image versus the ramp image. Last class also we have shown this image, that this is a very dark image, and suppose this is the white part, because to show the white part I cannot put, so I put some grayscale here. So, or you can have the, but this color is same and this gray value is same. So the gray values are same here, suddenly jump and the another gray values will be there, they are same at intensity level. So this is the ideal way to find out the edge of the object or the boundary of the object, but in reality you will not get. In reality you will be getting like this, that you have the dark image, suppose one color, then suddenly it gets changes and finally it achieves to the next intensity level. So you will find there is a ramp, a slope indicating the changes of intensity levels. Now these changes may not be due to the optical characteristics, may be due to the processing you have done, due to say you have done the average filtering on it to remove the noise, and as you know that as you are doing the average filtering, then there is a question of blurring will be coming, and that blur will give you, will be affected in your edge also, and that edge will become blurred. That means the texture, that means there will be, that effect will be here, and as a result this ramp will be created. Now the question of, once it is a blur, you cannot think that it is a single change of intensity. One pixel has intensity x, immediately you will not get the another pixel which is having y intensity. It will slowly change, and once slowly change means that image edge will be thick one. It is not on 1 pixel thick image or thin image. Now, what is the claim? That slope of the ramp is inversely related with the degree of blur. If the slope is very high, that 90 degree, that means sharp change, 1 pixel will get immediately sharp change from the previous one, and there is no blurring effect, right? It is a sharp change. And similarly, if the slope is very less, then the pixel intensity also will be changing slowly. So, that is why it is telling that it is slowly inversely proportional. So, more the slope, less the effect of the blur, and vice versa. And as you have the slope, obviously you will not get the thin edge, right. So, what is the edge point? Edge point is nothing but a point on the slope or on the thick edge, right. That is your edge point on the ramp. Edge point is a point which is lying on the ramp. Now, the set of such points will form an edge provided they are connected, right. Set of these points will form a edge provided they are connected. Now, thickness of an edge is dependent on the length of the ramp. Now, again length of the ramp is dependent on the slope of the ramp, right, because and slope of the ramp is dependent on the blurring factor. What it means that if this is the structure, what it means that this thickness of the edge here from here to here, that is the ramp length, and this is nothing but that amount of slope you have. And as we have mentioned previously, that it is inversely related with the blurring effect. So, it depends on the blur also. Suppose the slope is like this, that means thickness of the edge will be this much, right, and thickness of this edge will be this much, means that slope of this edge will be creating that information. As slope is reducing, thickness is, length is increasing, and as length is increasing, thickness is increasing. Is it clear? So, the blurred edge tend to thick, while the thin edge indicating the sharp edge indicating the thin. Oh, again this I do not know why it is happening. See, now if I take, suppose this is the slope, then first derivative will look like this, and while I take the second derivative, something like that, right. So, basically in the second derivative case, you see that you get the 2 points. One is towards positive, it need not be this is a positive, this can be negative and this can be positive, depending upon the slope, downward slope or upward slope, right. So, you get the 2 points. Now, if I draw an imaginary line, so this point is known as zero crossing points, and this is very powerful. That will give you the center of the edge thickness, right. See, because I cannot have a generally, if I take the whole thick image, edge image, then you will be losing the effect of visual things. What you need a thin edge line on the image. So, how to get the thin edge line? Then you take the center of this point, center of this edge, thick edge, that will give you the thin edge. So, zero crossing will help you to determine the center of the thick edge. Now, how to get an edge point? So, obviously, you will be looking for a point in the image which has the higher intensity value compared to the neighboring one. That is the best criteria, right? That I will tell this is an edge point provided it has the intensity value which is higher than the neighboring pixels. Now, once you determine that higher than the neighboring pixel, you need to know how much significant it is, right? Significantly higher word I will be using, I think I have used the word, yes, significantly stronger. Now, this significant stronger will be dependent on a threshold value, right? You have to decide a threshold value by which you will be telling if it is higher than that one, then you will be considering it is a edge point, it is an edge point. Now, how to determine the threshold value? One possible way is that you take the average of the image intensity values, that can be your threshold value, and if it is above the threshold average value, then you tell that this is an edge point, right. This is one way you can think, but issue is that since you are taking the average one, there is a possibility that lot many points may come out as an edge point, which may not be true, right. So, there are several ways you can determine that whether that is a significantly larger than the threshold value or not. Besides that, if I see, think about the first derivative. Now, you get this type of thing will be there. Any point higher than this, you can tell that this is an edge point. So, that is the thing that points, two dimensional word I will be coming later on, points first order derivative must be greater than some specified threshold. So, if you take the derivative, then this must be higher than the threshold value, that is the thing. Now, why two dimension? We will come to the while we will be discussing later the two dimensional effect and other things. So, this is an edge detection structure that you have an image, and you see that if I determine these boundaries, then I can easily visualize all the objects. There are some cases you may find that object boundaries are not visible at all, but while I will be using the edge detected image, then it is possible to visualize all the things. Then see here corner points are creating problem, I think. See, this is the case where the illumination effect is there, and since it is a dark image, say here the object boundaries you are missing, right. So, you have to do certain operations to see that no, all objects boundaries should be available to you. Now, what are the different types of edges you can visualize? One is known as the step edge. Step edge is nothing but that you have the constant intensity value and suddenly it jumps to the higher or lower intensity value, and again it is retaining the constant, almost constant intensity values. So, this is an ideal situation, constant intensity value suddenly jump to the higher one and again retaining it. But in reality you will not get this one, there will be a noise in your image, so it will look like that one if you have the noise. So, example is that a binary image you have 0 and white 1 only, then you will get this type of 0 and 255 say, then you will get this type of sharp step edge, right. Ramp edge, grayscale image, I gave you one example in the first class or second class my lecture, that you have the grayscale image, and in the grayscale image you will not find that this is 255 and this is 0. You will get that a certain slowly changing the color from this to this, and as a result the ramp will come out, and if you have the noise the structure will look like this. Then the ridge edge is you will get very frequently. What happens? You have the constant intensity, suddenly it jumps and again come back and again it is retaining the constant intensity level, right. So, it may look like this one or this one, and with noise you will have the structure similar to this. There is a term roof edge, it is also ridge edge, but it is not suddenly sharpened. After a small time it comes back, it retains for a little longer duration, then comes back to the again constant intensity level. So, roof edge belongs to ridge edge only, there is nothing, only issue is that here it retains little longer period. Now, how to detect the edge? That is the most important thing. If I know the steps of detecting the edge, rest of the things will be taken care. You have an image, it must have noise. So, you must be able to first remove the noise. Otherwise, if you do not remove the noise, and if you introduce the next step which is known as enhancement, the noise also will get enhanced. And if noise get enhanced, the noise also will show as an edge. So, I do not want noise should be considered. So, first thing is that you smoothen the image, that means you suppress the noise. Now, if you use any noise removal algorithm or any filtering algorithms to suppress the noise, obviously image will become blurred. Now, once image will become blurred, then you need to enhance the image. So, you will be using some enhancement technique to enhance the image. And once you have the enhanced image, now you know that by seeing the enhanced image, you will find the boundaries are more highlighted compared to the background one, right? But that is the reason of enhancement. So, through thresholding, you can get the boundary and rest you can suppress, right. Now, you get only the thresholded elements, and these elements will form your edge map. Now, remember that once you do the thresholding, there is a chance of missing link. What happens that you have, suppose you have an object like that, and once you do the edge detection, after processing the first, second and third steps, you may find that these are missing, these links are missing, because it is dependent on the pre-assigned threshold, and pre-assigned threshold you cannot satisfy. If you bring down the threshold level, you will find that several other noise are coming, several small lines will be coming. So, this link will be missing because of the threshold value. If threshold I take lower than the desired one, you may find extra lines will be there which you do not want, but if you increase the threshold level higher than that, then there is a possibility some lines will be missing. So, there is a need of introducing something which is known as edge linking, that if there is a small difference between the link, no link between the distance very small, then you add it. Some technique is the line fitting or some, there are several examples are there. So, these are the 4 steps involved in it. First one is smoothing, second one enhancement, third is thresholding, and fourth is localization. So, the points, the edge point can be determined either by the local maxima minima through or maximum minimum of first derivative or the through zero crossing, right. That as you know that this is first derivative effect will be there. So, this local maxima and minima will give you the whether it is a edge point or not. And similarly, if I have the second derivative, then just a line, artificial line, if you draw between these two, you will be getting a zero crossing point, that will become your edge point. Now, let us consider that it is a one dimensional edge, because image is a 2-dimensional picture, but let us consider it is a 1-dimensional image. And then in that case, I have to obtain the first derivative, which is the formula is a straightforward formula, and you get fx plus 1 minus fx if h is equals to 1. So, the mass becomes minus 1 and 1. Here x is not at center, that for x means that the point where you will be computing the whether it is an h point or not. To make it an x centered, then it becomes minus 1 0 1, right, that is your mask. So, these are the different types of age we have considered. This is an example, do not consider this an image. Values are 12 12 12 12, then 24 24 24, that means you have an age 12 12 12 and then 24 24 24, like that is there. So, this is the intensity level 12 12 and this is for 24. And if I use that minus 1 0 1 on this mask is minus 1 0 1, then you will find this is your first derivative fact. And this is the downward step, that means 24 24 24, suddenly it has come down. So, it is a downward step age and resultant will be 0 0 0 0 minus 12 and then 4 zeros. This is the ramp age where it is increasing 12 15 18 21 24 24 24, and this is an ridge age where it is 12 12 12 12 24 and again 12 12 12 12 and so on. And the corresponding convolution or convoluted image becomes S1, convoluted with M, it gets this result, right. Now, think about the second derivative one, that approximate finding the maxima minima of the gradient magnitude by second derivative is df squared by dx squared. This should be here, I will correct it, equals to 0, but finding the 0 or finding that point, discrete pixel point, we may not be always possible. So, what do we do? We obtain the approximate value through 0 crossing, because just these 2 points and I am adding it, but it may not be exactly satisfying this pixel, it will be a neighboring one. And if I have the one dimensional image, you will be getting the value fx plus 2 minus 2 fx plus 1 plus fx, right. Now, you observe that is centered at x plus 1. So, I just shift it f double fx plus 1 minus 2 fx plus fx minus 1. Now, it is centered at x and the mass becomes that 1 minus 2 1. So, this is an example, you have the all 10s and suddenly all 20s. This is the first derivative, all zeros, then 10, then 0 0 0, but this is your second derivative one, and that 0 crossing is lying between these two, right. One of them you have to pick up as your 0 crossing now, because it is not, as I told you, that it is not a discrete, it will give you that in between something, in between is not possible, you have to select one of the integer. So, one of the things you will be considering. So, here the mask I have used that 1 minus 2 1 or what, yes. So, this mask I have used, and if I use this mask, that means this plus this minus 2 times of this becomes 0, then this plus this minus 2 times of this becomes 0. Similarly, if I consider this one, this plus this minus this, it becomes this, right, and so on. So, if you analyze these things, you will be finding that 0 crossing area will come at this structure, either it is plus minus or minus plus or plus 0 minus or minus 0 plus. For example, if we go back to the previous one, the 0 crossing is a minus and plus or plus minus area or minus 0 plus, or similarly the reverse one. So, these are the possible area where you will be getting your 0 crossing. Now, how to get that 0 crossing is the, because you know the now area where your 0 crossing is lying, right. The slope of 0 crossing you can obtain, that a and minus b, just you add it, that will be your slope, and that you will be using a threshold value to detect what is the pixel 0 crossing area, strong 0 crossing points. So, the standard way, okay, I will come to that later on. Now, suppose you have the effect of smoothing the derivatives, you have that image you have, though you are looking, you are feeling that this is a dark and white, but in reality the image is like this, that you have, it is a lot of noise, or pixel changes are there. Now, if I do the derivative of this, the derivative image will look like this. Instead of doing that your image like that, so I am using some filter, Gaussian filter here. So, H into F, the image will like this, it is a smooth one, but obviously blur will be there, because here it was a little sharp, but here it is a blurring effect is there, okay, but you will be getting it. Now, if since I have used this one, so if I take the derivative one, I must get back this one, so I get a smooth image, normal image or Gaussian image. But if I change little, now you have the original image like this, instead of using del x f h f x, it is equivalent side, approximate side, then this I am doing into f. What I am doing, that this is your f, this is an original image, and I have taken the derivative of your filter, this will look like this, I have multiplied this one with f, then it looks like that similar Gaussian image, but it is an approximate one, it will not get back exactly, because you know obviously you have not considered this one, and you have, right, you have some part you have not added. So, this is the original one and changed one, but it also obeys the similar properties. Now, this is a one dimensional image you have considered, but in reality it is not the case, because your image is a two dimensional one, and image is a two dimensional one, and so you have to do along the x axis and along the y axis, right. So, del f is del f by del x and del f by del y you have to do, or you have to obtain, and using this you will be defining the gradient, which is a vector, and which compose of the two components, one is known as magnitude, another is known as slope. The magnitude is nothing but the del f square with respect to x, and del f by del x square plus del f by del y whole square, and then you take the square root, that will give you the magnitude, and slope is nothing but tan inverse the del y by del f by del y slash del f by del x, and this magnitude will give you the edge strength, and direction will be obtained by the slope, right, edge direction is obtained by the slope. So, now how to obtain this value, because you know this is not an integral part, this is your discrete domain. So, your value that we have already shown that the value will be f of x plus 1 y minus f x y with respect to del x, and similarly with respect to del y it is f of x y plus 1 minus f of x y. But that is in the Cartesian domain. Now, you need to know what happens to the pixel domain, because pixel domain there is no x and y, you have an I and j, and x is, in your case, x is this direction and y is, because you are reading the image from this plus, right, y is here, y minus 1, y plus 1. But in the case of image, it is first row, second row, third row, fourth row, and so on. So, it is and row is pointing to your y and column is pointing to your x. So, correspondingly you have to change this one. It was here x plus 1 y minus f x y, it is I j plus 1 and I j, right. Similarly is the case with respect to y. Now, this is the more detailed way you can see later on. Now, what happens in that case? If you see that one, we have obtained f of I j plus 1 minus f I j and f I j minus f I plus 1 j. So, basically kernel is, or the mask is minus 1 and 1, and this side is 1 and minus 1, agreed, because that is the thing we have obtained. So, in reality it is finding that this point f of x I plus f of I j plus 1 minus f of I j. So, it is finding, basically it is trying to find out the value of these 2 points to estimate the because this square plus this square, the value of this square plus the value of this square will give you the thing. The difference between these points and difference between these points will give you the change. The difference gives you what? Difference gives you the change of intensity with respect to x direction and change of intensity with respect to y directions, that square, right. But it is not taken into account the change of, because this direction also there will be a change. It is not a bidirectional thing. He has taken unidirectional with respect to x and with respect to y. So, the better approximation becomes if you consider this point, right, and this point will be considered only when if you take this minus this and this minus this. So, that is the thing, f x y and f of x plus 1 y plus 1, and here you have taken f of x plus 1 y and f of x y plus 1. So, that will give you the effect or the change in the intensity here. Is it okay? So, that is known as a bidirectional approximation. So, using this bidirectional approximation, you have obtained several edge detected algorithms. First one is the Roberts method, and it is considering, suppose you have the image of this 3 cross 3 image, it is estimating this area, say he is considering this Z5, Z6, Z8 and Z9, and with respect to x, gradient is this minus this, and with respect to y it is Z8 minus Z6. So, as you know, the magnitude is nothing but square root of gx square plus gy square, that means square root of z9 minus z5 whole square plus g8 minus g6 whole square, right. That will give you the edge strength or magnitude, and you can, because you know it involves lot of square and the square root, you can also estimate by z9 minus z5 difference plus difference of z8 minus z6. That also will give you the difference operator value. Using this, the Roberts mask becomes minus 1 0 0 1 0 minus 1 1 0. So, because you see that one, that 1 z9 becomes 1, this is minus 1 and this is minus 1, this is, yes, this is minus 1, this is 1, and this is again with respect to y, this is 1, this is minus 1. So, 1 and minus 1. And now, the problem here, it is a 2 cross 2, and it is a very awkward way of estimating the whether a pixel is a H pixel or not. Reason is that there is no center pixel here. So, for any, what you are doing to estimate whether it is a pixel or not, H pixel or not, you will be doing minus 1 of this plus of this, right, with respect to gx, and similarly with respect to this also you obtain, and then you determine, and if it is a greater than some threshold value, you take the decision whether it is H pixel or not. But since it is a 2 cross 2 and it is a very awkward way of estimating the age, better way is that is it possible the odd sub-image size. That odd sub-image size will be, smallest one is 3 cross 3. It is not required that you have to consider 3 cross 3, you can go for 5 cross 5 and so on. And as you are increasing the 5 cross 5 or so on, that your convolution parameters, that you know that you have to obtain certain operation on this, you have to increase the computational cost. Further, that you will be losing boundary results, right. So, you have to be careful to select the size of the mask. The smallest one is 3 cross 3. Now, in order to obtain the whether it is a H pixel or not, it is considering that with respect to x direction, it will be considering the difference of the third and first column, first row, and with respect to y first derivative, y direction first derivative, you will be considering the difference between the third column and first column, right. That means, you have a 3 cross 3 sub image. So, in order to get the first estimated value of first derivative, you will be obtaining the difference between these two, and in order to get the first derivative approximation with respect to y directions, you will be getting the difference between these two columns, first and third columns. That means what? No weightage is given to the center pixel. It is taking care whether central pixel is an edge pixel or not, that is determined by the other pixels, not himself, right. So, in general, the structure is like that. If you have 3 cross 3 neighbors, these are the pixel values and this is the center, and you want to know whether this is a edge pixel or not, what we are telling, that we have to obtain this partial derivative of this. Instead of doing, we are defining the mask now. The mask is nothing but A2 plus you give some weight to this A3, C into A3 plus A4 minus A0, C into A7, C is some constant plus A6. So, initially we started with the idea that difference between the third and the first columns, or difference between the third row and the first row. Now we are changing. What we are doing, telling that not only difference, we give little extra weight on the row or column where your pixel is lying. So, Mx is A2 plus some value here, third column, plus this minus this multiplied by this C times and so on. Now, here you observe that I have given the same constant multiplicator. Why same constant? That it is expected that if there is a constant weight you are giving here on this intensity, same weight, because there is only one pixel distance. So, change will not be very large, significant. So, same constant will be there, right. Similarly, this direction also, we are giving the same constant. Now, if as I change the value C, what it indicates? The C gives you that how much weightage you want to give on the vertical and horizontal pixel intensities. Basically, you see that I am giving the weights, extra weights on this. Am I right? So, these extra weights give you the indication how much weight I want to give to the vertical and horizontal directions, and how much less weightage you want to give towards the diagonal directions. So, as if I put C equals to 1, you get one edge detector, which is known as Prewitt operator, and if I put C equals to 2, then you get the Sobel operator. So, come to that original algorithm, what I told, that how to detect the edge. So, first is that you use some filter to smoothen it. GXY is your filter, right. So, you have used the filter convolute with convolution fxy with gxy to get the smoothed image. Now, this smoothed image, you use your mask, that whatever Sobel operator or Prewitt operator, you use it to get del f by del x. Similarly, you get del f by del y. So, once you know the del f by del y, then I am just adding them with absolute value, right. I could have taken the square root of, because I should have taken square root of this square plus this square, but it is a very costly thing. That is why we have taken just absolute value and then add it, and the direction is given by tan inverse of this. Now, if this magnitude is greater than threshold, then you tell this is an H point, right, and from that H point you can, using your direction, you can determine in which direction your edge is moving. So, this is an example how to compute the pirouette through pirouette operator. This is a 3 cross 3 and the numbers are 38, 66, 65, 14, 35, 64, 12, 15, 42. Now, I have deviated. See, you observe that I have taken what, 38 minus 12, 38 minus 12 divided by 2 plus 66 minus 15 divided by 2 plus 65 minus 42 divided by 2 and then total divided by 3, right. Or I have taken this minus this plus this minus this plus this minus this divided by 6. Now, why I am dividing by this? Because I need to normalize also, because the intensity values, if I do that, or otherwise if you do not have the normalized effect, then it will be variable, right. So, you do not know where it will be increasing, where it will, then threshold will not work. So, to use the proper threshold, you need to normalize them. So, normalizing factor is by 6, because here you are taking the two values, two intensity value, and finally you are adding them by 6, 3 values. So, again I am dividing by 3. So, that is why it is divided by 6, and theta is as usual tan inverse 16 by 18 and you get the 42 degree. This direction is 42 degree, and the other difference or edge strength is 24. This is an image with respect to derivative with respect to x, you get the image like that, and with respect to y you get another one. Now, if I add them and after that through thresholding you get your image looks like this. Now, you observe there are several noises are also there, even though you have used the smoothing algorithm, whatever the noise will be there, then edges are disconnected, it should not be there, it should be connected edges and other things, right. You can find out in the case of here, they are disconnected edges, but that is not correct one. So, we have to do something, we will discuss later on how to do it. We have discussed about the isotropic property, means that it is maintaining in all directions the same similar structure. So, this is one example. Now, what we have done, if you see that in the Sobel or pirouette operators, it is your values are with respect to x direction or y directions, right, vertically or horizontally. It is not taking into account the diagonal effects. So, if I consider the diagonal directions, then it is the mask becomes 1 1 1 minus 1 minus 1 minus 1, and similarly this side. Similarly is the case with the Sobel. You have the several examples. These examples are available actually, because it is not showing here. So, those things will be added. So, what do you get with the edge detection? Major problems are that it is very sensitive to the noise. As noise is increasing, right, the edges also you will find that your system is not able to detect the edge properly, because the noise will also the edge also will be shown on noise. So, you need to design an algorithm which will suppress the noise, right. Then it will, this mask will be producing the thick edges, because if you see that it is considering that minus 1 minus 1 minus 1 1 1 1 that type of things. Further, you have smoothened the image, so thickness will be there, right, because you wanted to suppress the noise, and as you wanted to suppress the noise, it is creating what, that blurred image, and as blurred image is there, edge thickness will be there. Agreed? And also due to noise you will get some false edge pixels. So, original idea was that you have input image, then you have to use the detection, edge detection, you will get the edge map, you realize that no, this will not work because there exists noise and you need to suppress it, and in order to do that you have added a smoothing operations, right. And by smoothing operations you are suppressing the noise, but you are introducing another problem which is in giving you the edge thick image, right. But once using that through zero crossing, you will be getting the now the thin image through zero crossing, approximate thin image, and from there you have to determine your edge map. Now, how to smooth the image? First is how to smooth the image, right, and then you get the edge detected map. So, there exist the two operators which use the smoothing. We will be discussing this one we will not be discussing today, because he is still in different mode. So, they operate. Now, suppose I give you deadline is 5 o'clock, will there be any change? No change. So, there is some problem with the system, there is some problem. So, there exist the two operators which use the smoothing. One is that Mar-Hillrath operator. It is a very simple one. What it does, first I will use the Gaussian filter to remove the things, and then I will use the Laplacian on the Gaussian filtered image, and that is why its name is Laplacian of Gaussian, LOG, right. So, Laplacian of Gaussian function is nothing but first you use the Gaussian filter to smooth it, and then use the simple Laplacian operator on the Gaussian filtered image. The other one is the Kenny edge detector. You remember the Laplacian operator, in last class we have discussed this thing for to sharp the image, and it is nothing but del square fxy by del x square is the two dimensional one, and del square fxy divided by del y square, and the equation is, if I expand it, you will be getting that f of x plus 1 y plus f of x minus y y, f of x y plus 1 plus f of x y minus 1 minus 4 times of f x y. That we derived in the last class, that it is coming that 1 0 1 0 minus 4 0 1 0 1. Remember, right? That was there. Now, we also discussed what is Gaussian filter. Gaussian filter is nothing but e to the minus e to the power minus r square. R square is nothing but x square plus y square divided by 2 sigma square. Now, this sigma is the filter parameter, how much filter you want to perform. Now, if I take the second difference on this, then I will be getting this. Is it correct? Just take the derivative and then for second derivative, it should be correct. Just not this one, I have used this one. Just first derivative of this and then second time derivative. So, you know, derivative of the function of fxy, and then twice you have to perform. Then obviously, this will come sigma to the power 4 term, sigma to the power 4 term, because in the book it was 2 sigma square. So, I was in, so most probably it will come sigma to the power 4 minus r square by minus r square by sigma square sigma to the power 4 e to the power minus r by 2 sigma square. So, now what happens that this is this will give you a mask. That mask if you use, then it will first filter the Gaussian with respect using the Gaussian filter, and then Laplacian operator is used to sharpen the image. Now, since Gaussian is a linear operator, this is also a linear operator. So, overall is the linear operator, and instead of initially we started with that you first convolve with respect to the Gaussian filter, then you convolve with respect to the Laplacian filter. Here what we are doing, no, I obtain the combined one, that combined one you use to convolve the whole image. So, convolution, I do not know whether how, that 5 cross 5 Laplacian Gaussian mask is given by this, whereas 17 is 17 cross 17 is a big one. So, if you perform this through filtering and then zero crossing, now how to obtain the zero crossing we will discuss later on. So, see what happens that this Laplacian of Gaussian del square gxy can be defined as del of dy square gy into gx plus gy into, this is a simple standard formula of derivative. Now, I am passing through, because you have to convolve with Ixy, because original image is your Ixy. So, this Ixy I am convolving with this one, then I am convolving the result with Gxy. So, I get the result here, and similarly Ixy I will be convolving with Gy, and then resultant will be convolved with del xy gx. The resultant, these two resultant images you will be adding, because this is a formula I am writing, the gx plus gy. So, that is the thing I am adding to get my LOG image, right. So, this is the steps involved. First, what we did, convolve the image with the second derivative of Gaussian mask along with the column, and then you are convolving the resultant with the Gaussian mask gx. The resultant image is Ix. Similarly, you are doing with respect to y, and then Ix plus Iy we are obtaining to obtain the Laplacian of Gaussian image. This is an example. Now, the zero crossing approximation, basically that is the important thing, how to estimate now zero crossing, right. So, this what you can do, that there will be some negative values, some positive values. That is the thing in the case of second derivative. You will be getting the second derivative, you will be getting some positive value, and then you are supposed to draw the lines. Then the point which is touching your x axis, that will be your zero crossing things. So, what instead of doing that, where all negative values I am making it dark and all positive values I am making it white, right. So, you will have that dark, then white, and then dark, and so on. So, now this is the area region, this is the region where it is a dark, there is a change of compositions, that is the region is you have the zero crossing area, right, and the middle of that you consider one of the point as a pixel point which is known as H pixel point, right. The zero crossing occurs between the positive and negative values of the threshold at LOG. So, all negative you put dark and all positive you put white, then it will, you will get the dark, white, dark, and so on. So, in between the all white, some position you consider that is a zero crossing element. See, now you know the two methods, one is the gradient method, another one is your zero crossing way. Now, in the case of gradient method, you see that it works very well when there is a sharp change of intensity level, the gradient method works very well, but when there is a ramp, slowly it is changing the intensity, you will find that zero crossing helps you very well to detect the edge points. See, here it is a step edge, the sharp change from 2 to 8, and you see that this gives you the area 666 and minus 66, straight away you are getting. But in this case, it is a ramp image, and in that case your value will be 3 0 minus 3, and you will not be able to detect straight away through gradient method which one is your pixel, H pixel, but through zero crossing, because this is the zero crossing area, you will be getting your pixel, H pixel point very easily. So, zero crossing gives you thinner edges, because it is the center point you are taking, you will be getting the thinner edges. It reduces noise, but it takes time, because a lot of computational thing involves, and in reality we use the gradient method. This is an example where LOG behaves poor in the corner. See this corner effects. Right. So, sometimes we may not need the corner components, then LOG gives you the better, but it needs lot of, because obviously your mask will be size 5 cross 5 minimum. In the case of Sobel and others, you need 3 cross 3. Here it is 5 cross 5, it needs more computational compared to that Pruitt or Sobel. Now, LOG can be estimated through difference of Gaussian, which is known as DOG. So, here LOG, that del square G is nothing but the difference of the two Gaussian filters. Now, these Gaussian filters are dependent on the value of sigma, as we told. The sigma gives you the filtering operations. So, this is the sigma is 1 and this is sigma is 0.3, and this gives you the sigma is the difference of these two operators, and then you see the behavior looks alike, right. So, generally that ratio of sigma and sigma 2 is generally, it has been found that 1.6 gives you the good estimate for the approximating that del square G. And obviously, that whatever edge detector we have discussed till today, all of them are having the problem of linking between the two. There is a chance of gap between the same edge, but in between there may be a edge will be missing. So, there is a need of some edge linking algorithm.